Hi, my name is Steve Ward, and I'm going to talk about alarm management in HMI and SCADA applications. So what is an alarm? An alarm is an exceptional event that must be reported to and usually acted upon by the operator. So it could be a level is too high, a temperature is too low, an equipment has failed, or some other issue. This is different from an event. An event is something that may be of interest but does not require action by the operator, or it may even be the result of an operator action. For example, the shift has started, a set point is performed, or some other operation that would be a normal part of the equipment operation that's interesting and needs to be logged or reported on, but doesn't actually need to be acted on specifically by the operator. So the history of alarming is that traditionally alarm panels comprised of lots and lots of annunciator lights that came from discrete or analog sources. In the past they'd have used physical lamps, later they used LEDs, which were a bit more reliable, but either way these were very expensive to create, very difficult to create and modify, and also very difficult sometimes to see what was going on because of the sheer volume of lights that were on the alarm panel. If you think about something like a power station or other large application, this could be a bank of lights covering an entire wall of the control room, and if one light came on, an operator might miss it or not see what was going on. So useful, but not ideal. Alarms were often also printed to a line printer as an indelible record, but if you were getting lots of alarms, then that could result in a very large printout, and then it became difficult, if not impossible, to actually go through all those pieces of paper and find out what the actual alarm was. Useful maybe for recovery and testing after a severe disaster, but not really very useful for day-to-day purposes. So in modern alarm systems, we use a HMI SCADA or the operator screens of the distributed control system, and those are used for alarm display. And in parallel, we also log to a database so we can have historical views and reports. And this is all done electronically on modern computer systems, which makes it much easier to handle and manage the alarms. As an aside, some systems also have the alarms generated by and managed in the PLC. So this is quite common in distributed control systems. And another benefit is it means you can get controller time stamping. So in some large systems, you need very accurate time stamping for the alarm. You need to know exactly when it occurred. For example, in electrical systems, if a circuit breaker trips, that can cause multiple alarms from downstream circuit breakers. So what you want to know is you want to know the first up alarm down to a level of maybe 1 millisecond. And the best way to do that is inside the controller. That can also help in distributed systems as well, where maybe you've got multiple client HMI SCADAs and then you want to have a single view of the truth. So if you manage the alarms in the controller, it makes it easier just to know exactly where the alarm comes from and what the current state is. So that's on top of any normal alarm handling. It's an additional function, and it just distributes where the alarm is actually generated and how it's actually the current state is controlled. So there are two main alarm types, discrete or digital alarms. These occur when an alarm is generated on a transition to an on or off state. So for example, it might be a switch that turns on to indicate that now we're in alarm condition, or it might be a switch that normally has to be on. Maybe that's an emergency stop or some sort of gate signal, and as soon as that goes off, that indicates an alarm. The other type is analog. And with analog alarms, we can have multiple types. So we could have a level alarm. A level alarm is where we compare the alarm value against a fixed value, and we generate the alarm if the value is above or below that fixed value. So we could have an alarm, imagine a tank. The alarm for low level could be below 10%, and we might have an alarm for high level above 90%. We could also have rate of change alarms. Maybe the tank is filling too fast or emptying too fast, so that could generate a rate of change alarm. So we look at the amount of change over a particular time, and if the change exceeds that time, that's when we generate the alarm. And also, as well as having a level alarm against fixed values, we can have a deviation alarm where the alarm deviates from a set point. So for example, again, consider the tank. We set the set point to 50%. and then maybe we generate an alarm if the alarm is above 60% or below 40%, so effectively more than 10% away from our desired set point. In most systems, the levels can be changed, but in some systems, particularly validated systems and safety systems, the alarms may be fixed in terms of what the levels are due to the nature of the validation of those systems. It's also possible to have multiple levels with analog alarms. So for example, you might have a low alarm, but also a low alarm. So you generate an alarm below 10%, which warns the operator that they need to start thinking about taking action. But then you generate a critical alarm, the low alarm, below 5% when your tank is getting very close to empty. We can also have high and high alarms. Again, maybe you generate the high alarm at 90% to indicate to the operator the tank's getting very full. And then another alarm at 5% to say, look guys, the tank really is getting full now. You really need to do something about this. So multiple level alarms just give the operator a bit more notification of what they might need to do in terms of taking action about the state or value that's been exceeded. So we do have a system for alarm evolution. In general, the alarm starts off in the normal state, which means there's no alarm. So this should be the usual state for the system. Everything is running normally and there's no alarm. It's all operating normally. As soon as an alarm is generated, then it enters the alarm state, and that's the generation state of the alarm. So the alarm transitions into the alarm state and it's been generated. And the next step would be the operator would see the alarm, and then they would acknowledge that alarm to say that they've seen it and that they're going to perform some action to rectify the alarm situation. In parallel with the user seeing the alarm and acknowledging it, we also get the possibility that the alarm could be reset and returned to normal. This could be after it's been acknowledged and seen by the operator because the operator's taken some action. For example, if our tank is filling, maybe the operator reduces the filling speed and then that stops the tank from getting so full. And in that case, then the alarm would return to normal as a result of the operator doing something. But it's also possible an alarm might occur and then reset by itself, maybe because of automatic control of the system, which generates the alarm and then takes action itself automatically. Or maybe it's an alarm which occurs and then goes away because of some other natural reason. So sometimes the reset can happen by itself, sometimes it can be a result of operator action. It could be then that the operator sees that it has been reset and then they would acknowledge it, and then at some point you need to delete the alarm from the alarm list. So typically the alarm can either be removed manually or it would be removed automatically after it's been both acknowledged and reset. Now, not every application needs every state. This behavior may be customized. Some applications might not need the acknowledgement. They might just have a reset state when the operator actually performs the action they need to. Some alarms might not need resetting. That would be deleted at some other situation. But typically these are the 5 normal alarm states for alarm evolution. To relay the alarm information to the operator, we have some form of alarm displays on the HMI SCADA screens. In many HMI SCADAs, there's an alarm banner at the top of the screen. This shows the latest alarm, so it's typically one line only. Maybe it will be filtered for the area or process related to that screen, but often it's just an immediate view to the operator of what is the latest alarm in the system. The alarm banner doesn't have to be at the top, it could be elsewhere, but in many systems I've seen, that's where the alarm banner would be located. What you would then have is additional screens. There would be a dedicated screen for a current alarm list with all of the current alarms that are active right now. And that would include buttons for the operator to acknowledge alarms and possibly to reset or delete alarms as well. Typically that list can be filtered, so the operator might want to filter by time, by severity, maybe by plant area, depending on how the alarm list works, or maybe other criteria. And then you have a historical alarm list. Again, this is typically another dedicated screen. This has a list of historical alarms. So this time there are no buttons because the alarms have already been through their different states. They can't be modified now. But there is filtering again for the operator. And often this is also a higher level view used by additional people besides operators. So maybe it's used by quality teams. Maybe it's used by people doing digital transformation and continuous improvement. But looking at the historical alarm list and filtering it can help people understand what's happened with the system, and then they can perform action on the system to make improvements of whatever they need to do. Alarm display lists are often highly flexible, and typically they will include a few or more or all of these following lists. So we have the generation, time and date. There would be the tag or variable name. There would be an alarm description. There would be an alarm severity. If the alarm has been acknowledged, we may display the acknowledged time. And if it's been reset, we may display the reset time. Often there's no point in displaying the deleted time, at least not on the current alarm list, but that could also be displayed on a historical alarm report. We might want to display when it's deleted. And in the current active alarm list, we'd also want to display the state. Is it active? Is it acknowledged? Is it reset? And so on. There may be additional information we want to display, maybe where the alarm was generated from, the name of the computer or the server. Maybe we want to display information about who acknowledged the alarm, so who the operator was and what group they were in. So that there may be additional information depending on what's required. But of course, the more information there is, the harder and harder it gets to read that alarm display list. So typically for current alarms, we try and minimize the amount of information to the operator to make it as quick as possible to read. To further help the operator, we can also color code alarms according to requirements. So maybe alarms of different severity have different colors. Maybe we have different colors for what the alarm area is, where it came from. Or maybe there might be other colours for other reasons as well. The idea is to have colour codes so that the operator can see certain colours and know what action to take. Typically, colours are associated with heat. So green is normally normal, or maybe blue, they're sort of like cooler colours to indicate that not too much is required. Green is often associated with normal. Orange would be a warning, and red would be an actual alarm state. But some people have different colours. Sometimes red means that something might be in a normal state, and green means that it's actually active. So a bit like traffic lights. Red is stop and you don't do anything. Green is go and you need to take action. But in my view, that's rarer. Normally the colours are blue or green for normal, orange for warning, and red to take action. And as an additional alert, you may even flash the alarms as well. So alarm that's just come into the system and hasn't been acknowledged yet, maybe that's flashing red and black just to tell the operator that something's going on and that they really need to take some action. So as we've said, for the alarm display on the HMI SCADA screens, to make sure that the operator is alerted, there may be various functions we can do. And these can actually be performed on the Mimic screens themselves, not just on the alarm display, but actually on the Mimic screens themselves that are showing the operator the plant status. So we may have objects that change colour. Again, red for alarm, orange for warning, blue or green is normal. So you might have a display of a pump, and that could change colour according to the alarm states. Maybe you want to display additional status on top of the screen. So an alarm could be indicated by a warning sign that is overlaid on top of an object. Again, we've got the alarm banner at the top of the screen, and you may also play warning sounds. For example, there could be a beep which comes on, and that could be a continuous beep or continuous warning sound like a horn. Or maybe you want to play a sound file, and the sound file could be some music or a particular sound, or it could even be a human message that tells the operator what's going on. If you've ever watched some of these flight disaster type programs, you'll see a warning that comes from the cockpit, like warning terrain, which tells the pilot that the plane is getting too close to the ground. So you might have some similar approach in the HMI SCADA system, where you could record a sound and tell the operator exactly what they need to do. So warning, tank level too high, for example. Not too common for me to have heard those sorts of alarms. Normally it's a beep or a sound. Sometimes there might be multiple sounds. But if there are too many sounds and too many things going on in the control room, you can actually end up confusing the operator. And I've also seen alarm systems where they've silenced the alarm just because it gets too annoying and the operators will want to focus on what they're doing without being continually interrupted. So since we often have a computerized HMI SCADA or distributed control system, it's very common for alarms to be logged to a database so that we can have historical views and reporting. Those reports can be used for alarm analysis after the fact, and they can be used for continuous improvement. So very common for that alarm to be put into a database. Sometimes that's used like a black box. So a black box flight recorder, just like in an airplane, you just record all the alarms regardless whether you know you're going to need them or not, just in case. But often those alarms can actually be a useful report to tell you what's happening in the system. And by reviewing those alarms and analysing them, you can actually take action, and you can perform your continuous improvement or look at particular issues and resolve those issues to help your operations. Here's an example of what a HMI SCADA alarm log record might look like. So you can see we have a timestamp. We also have a sequence number in this case. It's common in databases to want to have a unique ID for each alarm. So that could be your sequence number. You see we have an alarm ID. We have an alarm class, which is the severity of the alarm. We have the area or resource where the alarm comes from. We have the process or user that logs the alarm. There might be some additional reference. That could be the computer again, or some additional reference. For many systems, particularly validated systems, you want to know that you're not missing any alarm records. So it's very common to log the previous state as well as the action that caused you to log this alarm, and then a final state as well. So by doing that, that ensures that you haven't missed a step, and you can make sure that when the alarm goes from normal to acknowledged and then to reset and then to deleted, you can make sure that you're not missing any steps by using these three columns. There's an alarm message, and the alarm message can vary on the capabilities of the system, but typically that's a human readable message that gives the operator enough information to be able to respond to the alarm and do something about it. And then we have the generation time. The generation time might be different to the timestamp. Typically the timestamp is the timestamp in the computer where the alarm is logged, but the generation time might be the time in the PLC where the alarm was actually generated. But it depends on your system. For many systems, the HMI SCADA is performing the alarm logging. So in most systems, the timestamp and the generation time would be the same time. Another aspect about timing is typically 2 times a year we change from summertime to wintertime for daylight savings. So you may also have additional time columns for the local time and the universal time coordinates. So universal time coordinates, that's based on UTC, what used to be called GMT, Greenwich Mean Time, often known as Zulu time as well. The benefit of coordinating against GMT or UTC is that that doesn't have any daylight saving times, so you get an active and actual absolute alarm time. Whereas if you're using the current local time, then 2 times a year you might find either there's a 1 hour gap when the clocks go forward, or when the clocks go back, you might even get duplicated alarms because the clock goes back by 1 hour at that time of year. So that's an additional aspect with timing, is additional columns for local and UTC time. So having the alarms logged into a database, we can now generate a report. Reports typically replace alarm printing in most applications. Very rare to see a printer now. There may be a few older applications where printers are still present, but in most of the applications I've seen, the only reason for having an alarm printer is to print out the report if someone wants a paper copy. But even that's getting rare. Normally reports are generated into a neutral format like a web page or a PDF file, and then they can be sent electronically by email or placed into a file location where people can access those reports. And that typically replaces any legacy printing of alarms. Those reports can be generated on a regular basis, maybe every hour, maybe every shift, maybe every day. Or there might be a situation where someone wants to create a manual report, so that user would be able to enter the start and end times and then generate that report. And often there's additional filtering. Maybe users only want to see certain severity of alarms, maybe users only want to see a certain alarm area. So filtering the alarm allows them to produce the report that they need to see for whatever purposes they're doing. For continuous improvement, a common alarm report is a Pareto or top 10 report. So a good alarm report would be top 10 by duration. That would give you your main alarms which cause you your most alarm situations, particularly if that's causing downtime. If you can work out what your top 10 causes are that cause you the longest duration of alarms, you can then work on what's causing those alarms, and then that can give you a good route to reducing the downtime of your machine. This is very common also when we're looking at overall equipment effectiveness, to be able to look for these breakdown reasons. So top 10 by duration is very useful. Eliminate the alarms which cause the longest shutdowns or the longest issues. And the other one that's also very useful is top 10 by occurrence. So what you might get is you might get lots of alarms which only occur for a short time, but then overall that can lead to a lot of particular instances. So by eliminating those top 10 by occurrence, that can allow you to perform considerable improvement to your machine or your process just by reducing that type of alarm. And then in a typical continuous improvement approach, you would then repeat that. Having reduced your top alarms, you would then attack the next top alarms and so on, and that would allow you to continually improve your machine. And there's no prescribed way of actually performing that continuous improvement. That would be down to what the particular process is. Is it an issue with the raw material? Is it the machine itself is unreliable? Is it maybe the operators need more training? Or are there some other external aspects which need to be taken care of? So again, the reason for doing that continuous improvement and having the alarms, it just enables you to take those decisions and then perform that continuous improvement, and that will be unique to each application and process and machine. So a big topic is alarm optimization. It's common when designing a system to generate alarms for every single thing that can go wrong. That's a great idea because you want to have some notification that the operations aren't performing as they need to. But what can happen is, over time, people add more and more alarms because there are problems that need to be tracked. And what can happen is the operators can be overwhelmed with too many alarms. I think a good guideline is 2 or 3 alarms per hour. If you've got a lot more than that, then that's probably too many. And if you've got less than that, then that's good. But then maybe you could add some alarms because maybe there are events or things you're missing where you could actually respond to those to improve your operations. But remember, your operator has to be able to respond to this alarm. Then something has to be done about the alarm. Maybe it needs for a maintenance engineer to go out and perform a fix. Maybe it needs some adjustment to the machine. Maybe it needs some retooling or replacement of raw materials or other components. So if you have too many alarms, then that just means that the operator can't cope with the volumes of alarms coming into the system. So the actual number of alarms will vary from case to case, but 2 or 3 alarms per hour would be a good number for the operator to be able to act on, and also still have them being able to perform their usual activities. So if there are too many alarms, then what you could do is you can optimize the alarms, and this can start off by performing a review of alarms. How many alarms are you actually getting? What types of alarms are they? What's causing those alarms? Maybe this is part of your continuous improvement approach. Can the alarms be handled? Are there alarms which should be events? So what you do is you look at all the alarms and then try and optimize them initially by then performing a set of actions. So we could start off by prioritizing alarms. Maybe we've got critical alarms that need immediate action by the operator, but there might be other alarms which are low priority and which the operator doesn't need to immediately act upon. So you might get an alarm that warns you that the tank level, as we mentioned earlier, maybe it's going above 90%, but it's not reached 95% yet. So that's maybe a worthwhile alarm to track, because if it keeps happening, that could indicate that maybe your tank level is getting too high. On the other hand, if it's just getting above 90% but not reaching 95%, maybe your alarm limit is set too low and you may to increase your alarm limit to reduce that alarm from occurring. So what you can do is you can create alarm views that reflect the priorities of your machine or process. So there may be particular areas which are more critical than others. There may be particular types of alarms that you need to have more focus on. So you can create your alarm views for that reason. You can then route alarms by plant area or by process area. Often you only want operators to see alarms which they can actually act on themselves. So in your main control room, you might have an operator that's responsible for a particular area of a plant. So on their workstation, they will only see the alarms which are appropriate to them. And if you're down on the plant itself, if you have the HMI SCADA operating a particular part of the plant, typically you'd only want alarms for that part of the plant to be displayed. So another thing you could do is apply alarm blocking. So what this is where you have high priority alarms which prevent low priority alarms from being triggered. This is a common issue I see. You get one alarm is generated and it causes a flood of alarms because that one event is also causing other events. For example, if a master circuit breaker trips, then you might get lots of alarms to say the machine has gone slow, something's not happening when it should do, some outputs are now failing, and all of those are caused because you've had a main power failure. So of course the main power failure is what's causing the alarm. So in that case you wouldn't want all those other alarms to be triggered. So alarm blocking is where preventing those other alarms from occurring once the higher priority alarm has occurred. And there's a standard for this. It's called ISA 18.2. Now, if you're getting an awful lot of alarms, you might want to remove those alarms completely and categorize them as events. So they could then be stored to an event table rather than pushing to the alarm table. So again, for example, if a tank level of 90% is not too bad, and it rarely goes to the higher alarm of 95%, then maybe you just recategorize that 90% alarm as an event rather than the alarm that warns the operator. You know, it's all very well warning the operator, but if they never have to do anything about that because the system always corrects itself, then it's no longer appropriate for that 90% level to be an alarm. Another option then is to also route alarms to appropriate personnel. So maybe the alarm doesn't need to be going to the operator. If it's a maintenance alarm, that could be sent to the maintenance team rather than the plant operator. That could even become an event where you trigger a computer maintenance management system to trigger that automatic maintenance request rather than have an operator have to do that themselves. Again, repeating alarms, you might want to modify the alarm configuration there, maybe even the PLC logic inside. You might want to remove those alarms so they only report once and not continuously every time they appear. So this is common when we're monitoring analog values. It's quite common for there to be ripple on analog values. For example, consider that tank level. We've set the alarm limit at 90%. The alarm might be going off every 90%, but the actual level might be rippling between 91 and 89%. So every time it goes from 89 to 90 and then above, the alarm is triggered, but actually it's only one alarm, but because of that ripple or oscillation, we could see that alarm is repeating. So maybe there would be some PLC logic, maybe some alarm configuration, maybe we could set some sort of deadband in there, or some hysteresis, and that way we can prevent that alarm from continuously appearing every time it appears and have it only reported once when the main occurrence starts. It's also possible then to create alarm and event reports based on the optimized alarm system. Yeah, we already mentioned this before. Yeah, we can create those Pareto or top 10 alarms. And it also might be then possible to modify the HMI SCADA screens based on what the optimized alarm system looks like to make sure that only the critical alarms are reported to the operator. There's a common movement now for flat HMI screens. We did some work with user experience and user interfaces when we were with GE, and what they were doing is they were making all of their screens very flat and muted, typically a grey screen, maybe a few colours but very minimal, and the idea is the operator can look at that screen, and if everything is grey or flat, they don't have to worry about everything because it's all in control. As soon as something goes into the alarm state, then you would change the colour, and then they would see a box that they need to take action on. So maybe it's something goes orange or red, like I explained the colour codes earlier. But when they've got just a grey screen, they can glance at that and say, nope, nothing to worry about. Contrast this with older HMI SCADA screens, which could be a mass of colours. So there would be red for something that was stopped, green for something that was running. There would be lots of different colours, maybe a dial, for example. I've seen dials which have multiple colours on them. You know, red at the top and bottom for the high and low states, Then you also have orange for warning states. There may be green, and there may be different shades of green depending whereabouts the process needs to be. That might be appropriate for a detailed screen, but you don't want to see that at a high level screen. So you modify your HMI SCADA screens to make them suitable for the standard operator conditions and to avoid overloading the operator. Another possibility is to perform alarm dispatching using email or SMS or voice over IP. The idea there is that when there's a critical alarm, rather than that appear on the screen and the operator have to act on it, you could actually send it again directly to the person who needs it using an appropriate electronic technology. So most people are carrying mobile phones, so SMS is a good idea. Voice over IP if you want to actually relay a message to someone. An email might also be appropriate. Just bear in mind that, of course, not everyone is monitoring their email all of the time. And then again, we've got that Pareto or top 10 principle there to eliminate the most occurring, the longest duration alarms. And you also might want to cross-reference against cost. Maybe you're more concerned about cost of your process, so you might want to look at what are your most expensive alarms. It could be an alarm occurs a lot of times, but if it's not affecting the quality of the product, or it's not affecting the actual operation in terms of being able to make whatever it is you make, maybe that's again something that could be downgraded to an event or a low priority alarm. But what you do want to focus on is expensive alarms. So typically that's anything that stops the machine, so a breakdown condition, or anything that affects the quality of the product such that you can no longer sell it to your users. So often, again, we'd do that top 10 analysis, eliminate those types of alarms, and then you'd repeat that process to continually reduce downtime and improve productivity.